Afternoon will be Masaki Tsukamoto from Kyoto University, and he's going to talk about the rate distortion dimension of random Brody curves.
Thank you. And I'd like to thank the organizer for giving me this wonderful opportunity. I'm very happy to talk in this conference, so celebrating his birthday. I visited Alex, I think in 2012, so more than 10 years ago. And I asked him many questions about just Brody curves, and so he taught me a lot. So thank you, and happy birthday, Alex. Okay, so this is a summary of my talk. So my main purpose is to propose an ergodic theoretic approach to the study of Brody curves. What are Brody curves? Very simply speaking, Brody curves are one Lipschitz holomorphic maps from the complex plane TC to the complex projective space. And my conclusion is that, very roughly speaking, Brody curves has an ergodic theoretic structure somewhat analogous to that of axon-wave diffeomorphisms. This is my main reason. Okay, this is a summary of my talk. Okay, now let's go to more details. So what are Brody curves? Let F be a holomorphic map from C to CPN, and F0, F1, Fn are homogeneous coordinates. We define its local Lipschitz constant, or sometimes called spherical derivative, by this formula. So it is very well known that the right-hand side of this formula is non-negative, so we can take its square root, and the square root is denoted by this, so the norm of df. So what are geometric meaning? Geometric meaning is very clear. So we have complex plane C and complex projective space, and we have some holomorphic map from C to CPN F. Then and take some point Z in the complex plane and tangent vector V at Z. Then this point Z goes to the point FZ, and the tangent vector V goes to DFV. And CPN has a standard metric called Fubini study metric. Then the Fubini study length of this tangent vector dV is equal to the spherical derivative times the Euclidean length of V. This is the geometric meaning of this a bit complicated formula. Okay, so now we can define Brody curve. So let F be a holomorphic map from C to CPN, and we call it a Brody curve if its spherical derivative is bounded by 1 all over the complex plane C. So in other words, so Brody curves are one Lipschitz holomorphic maps from C to CPN. Okay. But why is this interesting? Probably there are many reasons, but one important reason comes from the fundamental theorem of Robert Brody. So Brody proves that a complex projective variety is Kobayashi hyperbolic if and only if it does not contain any non-constant Brody curve. So Kobayashi hyperbolicity is some fundamental property of complex manifold, and Brody shows that it can be completely characterized by using Brody curves. So many people are interested in Brody. Any question? Okay. So today I want to study the space of Brody curves and the group action on it. Let be the space of Brody curves in CPN. So we consider all Brody curves in CPN. And its topology is given by the standard compact open topology. Or more explicitly, we define a metric E on this space by this formula. So F and Z are Brody curves. And this right in the right-hand side, this dCPN is the Fubini study length between 2 points in CPN. So we consider the Fubini study length between FZ and ZZ over the unit disk. Then this gives a metric on Bn. and its topology is a standard compact Ecklin topology. This is the space of Brody curves. And under this metric, this space becomes a compact metric space. And the important point for us is that it has a natural group action. The group C continuously acts on this space by this way. So it's just a translation. So this space and this action is classically called a normal family in the classical context of complex analysis. And Gromov began to study this group action from the viewpoint of mean dimension theory. It is a new viewpoint. What is mean dimension? So roughly speaking, mean dimension is a number of parameters per unit area of the plane for describing the orbits of this group action. Maybe so mean dimension is still not so popular in mathematical community, so I want to define its precise definition. What is mean dimension? By the way, is there any question so far? What is mean dimension? And for explaining the definition of mean dimension, we need to review some old idea in metric geometry. Let XD be a general compact metric space. Take some positive number, epsilon. And let F be a continuous map from X to some topological space Y. Then we call this map F an epsilon embedding. If for any point Y in the target space, its fiber has a diameter smaller than epsilon. Okay, the picture is this. X looks like some tube. And in this picture, Y is a plane. And we have some map F. And this picture means that for any point Y, its fiber is small. So in other words, if we ignore some small epsilon error, this map F looks like an embedding. This is the definition, epsilon embedding. Okay. And by using this notion, we define quantity called epsilon width dimension. We define epsilon width dimension of this metric space XD as a minimum integer n such that there exists an n-dimensional simplicial complex P and an epsilon embedding from X to P. Okay, maybe this looks a complicated idea, but basically it's a very natural idea. So general compact metric spaces are very complicated. So there are many fractal spaces. So we want to understand it by using some approximation. We try to approximate such fractal spaces by some combinatorial objects of simplicial complex. And the error of the approximation is bounded by epsilon. And we ask how many parameters we need in this approximation. This is the idea of this epsilon width dimension. And essentially, this definition is due to Rizzo in the early 20th century. Maybe this looks a bit complicated. Is there any question? Now we can consider mean dimension. So X is still some compact metric space, and in this case, we consider the group action on it. We assume that the group C continuously acts on X. Then any positive number R, we can define a new metric dr, so-called Bowen metric, by this formula. So this TAX and TAY are orbits of X and Y under this condition. So we try to measure the distance between two orbits over this time. So we have a family of metrics. Now we define mean dimension by this formula. this is epsilon width dimension of X, but with respect to this new metric dr. And we want to know the growth of this quantity with respect to the area of the R disk. And take the limit and take the limit with respect to epsilon. But it is known that this limit is always exist. And it becomes a topological invariant of this group action. The Gromov definition, mean dimension. Okay. So this is the end of the review of mean dimension. Is there any question?
It's of course possible that the limit is infinity, right?
Yes, of course. So the value is a non-negative real number and possibly infinite. Okay. So let's go back to Brody curves. So recall that we denoted by Bn as a space of Brody curves in CPN. And the important point is that this space has a natural group action of C. So this is a compact metric space and it have a natural group continuous action of C, so we can consider its mean dimension. And based on a result of Rx, Gromov proves that the mean dimension is bounded by 4n. This is a first result on this problem. And it had been an open problem. It has been an open problem for some time to improve this estimate. Okay, so I wanted to solve this problem, and so I need to introduce a new quantity called energy density. Let F be a Brody curve from C to CPN. And first we define its energy density rho F by this formula. This may look a bit complicated. So A is a point in C, and we consider the so-called Dirichlet energy over the disk R disk centered at A. And we take a Schupriman with respect to point A, and we divide it by pi r square and take the limit. Roughly, this just measure how much energy of F is distributed over the plane. And we define rho CPN as a Schupriman of this quantity over all Brody curves. Then it is known that this quantity is always positive and strictly smaller than 1, and it goes to 1 as n goes to infinity. Okay, so we have two quantities. One is a mean dimension, and another is this energy density. So then my friend Matsuo and myself prove the following theorem. So this is the mean dimension of the group action on the space of Brody curves. And this mean dimension is equal to 2n plus 1 times the energy density. Okay.
Can you go back to the previous slide?
So how? Okay, yes.
So for this rho CPN, do you know which F realizes it, or is it realized?
It's a non-trivial question, but it can be. So there exists some Brody curve F attaining the Schupriman. So this is actually maximum, but it's not a trivial fact because this rho F is not a continuous function.
Is it unique?
No, not unique.
But it's constructive.
But probably not unique. I do not know it.
It's not constructive. Is it constructive?
Not constructive.
You don't have a guess for what it is.
For n equal 1, I have a conjecture, but it's a bit different story. So today I want to skip it. Okay, so this is a mean dimension formula. So mean dimension is essentially equal to energy density up to some natural factor term. Okay. So this is one solution to Gromov's problem. But this is an old result proved more than 5 years ago, and the proof of this theorem is not a topic of today. So I want to study a new aspect of this theorem. But by the way, so the equation. Okay. So this is a new problem I want to discuss today. I want to, so this is our mean dimension formula, and I want to understand this formula in terms of invariant probability measures. This is a new problem. What it means. So next, so we want to study invariant probability measure on the space of Brody curves. So let mu be a Borel probability measure on Bn, and we say that mu is T invariant if we satisfy this equation for any Borel sets A in Bn and any complex number A. It's just a, so it's just a translation invariant distribution on the space of Brody curves. Okay. So maybe it is not so common to study invariant probability measure in the context of config curve theories. So let's look at some example. This is probably easier. So this example is maybe gives you some idea. So take some large positive number L and A. We define the lattice lambda by this way. So it's a very sparse lattice in the complex plane. And let D be a unit disk around the point A. And take some point W in this square of side length L, and take the sequence of points in this disk D, labeled by this lattice points. We define a meromorphic function FWU by this formula. So for essentially lambda is a lattice point, and we consider this simple rational function. Its pole is W plus lambda and some coefficients, and take the sum. And by appropriately choose these parameters L and A, we can check that the spherical derivative of this meromorphic function are always bounded by 1. So it gives Brody curves. So we have a family of Brody curves parameterized by these W and U. Okay, then which independently choose these parameters W and U lambda uniformly from the uniform distribution of this and the unit disk D. So in other words, so these parameters are random variables. Then these functions are random meromorphic functions, and they are all Brody curves. So its distribution provides some probability measure on the space of Brody curves, and it is easy to check that its distribution is translation invariant. So it defines a T invariant probability measure mu on the space of Brody curves. So in general, invariant probability measure on Bn correspond to some random family of Brody curves. Is it clear? Okay.
When you say in general, invariant probability measures
Okay.
correspond to, you mean all of them look like this? And
No. So in general, there is no closed formula. So this is just so conceptually just so considering measure is equivalent to considering some random functions. Okay. So now we define the MTBN as a space of all T invariant Borel probability measures on this space of Brody curves. Okay. this is so list. So this is the statement on our problem. So we want to express both sides of this formula in terms of invariant probability measures. And we start first. Well, sorry. First, I want to consider the right-hand side. This is easier. So recall that. So the rho CPN is the supremum of F over all Brody curves. And rho F is given by just some a bit complicated formula. And we want to express this quantity by using invariant probability measures. And actually, it's very easy. We define a continuous function C on the space of Brody curves by this way. It's just some natural factor times the square of the spherical derivative as the origin. This is a continuous function. Now we can prove that this quantity, so this is the right-hand side of the mean dimension formula, is equal to the supremum of the integral of this C over all invariant probability measures. So now we have expressed this quantity by using invariant probability measure. But what is the meaning of this quantity? Maybe this looks a bit. Actually, this is a very simple quantity. So what is the meaning of this integral? Let F be a Brody curve, and we define its Nevarlinear Schmidt R-force characteristic function by this way. So this is a standard object. And for simplicity, we assume that the probability measure mu is ergodic measure. Then, by using the pointwise ergodic theorem, we can prove that for mu almost every Brody curve F, the characteristic function has this asymptotics as R goes to infinity. This is this. So this term is a previous integral. And some natural factor term and R squared. So essentially, this integral describes the leading term of the characteristic function. This is the meaning of this integral of C. Is it okay?
Understood correctly, in that formula, you don't need that the curve is a it's much more general. This formula of the previous, much more general, you don't need to know that it's Lipschitz one map.
Oh,
Yeah, it's something evident.
we need Lipschitz condition. So not necessarily Lipschitz, one Lipschitz, but we need some Lipschitz condition.
For this formula, but maybe you don't need even pointwise condition, you need something
But
general.
actually, so here it's a translation invariant.
Yes, you need translation.
And if the measure is ergodic, actually it's essentially almost every function is Lipschitz. So has some Lipschitz constancy.
Yes, yes, yes.
Okay. So again, so this is a mean dimension formula, and we want to understand this formula by using invariant measures. And so now this right hand side becomes some mysterious quantity. Then next, we want to understand the left hand side by using invariant measures. And this is a bit more complicated story. And for this purpose, we want to use ray distortion theory. This is a fundamental theory introduced by Shannon in his monumental paper. So next, we want to so express a bit about ray distortion theory. Because that this our space Bn has a metric. Let mu be any T invariant Borel probability measure on Bn. And so we fix such mu. So here we fix such mu. And we randomly choose the Brody curve F according to this distribution mu. Then we can consider F as a stochastic process. And for any positive number epsilon, we define the ray distortion function as the minimum bits per unit area of C for describing this process within average distortion bounded by epsilon. If you already know the information theory, this is a very standard idea, but if you don't know information theory, this is a bit mysterious. So the example is actually this is a very simple idea. The example is JPEG, joint photographic expert group. Maybe most of you use every day in your smartphone. So in camera. So one JPEG. So what is how to say, so okay, so given a two-dimensional image, JPEG first expands this image in some wavelet basis and look at every coefficient, and then JPEG throw away small coefficients. Then the amount of bits becomes significantly smaller. This is what JPEG does. So, and in this process, so some coefficients are thrown away. So we cannot completely recover the original image, but the resulting image looks very similar to the original one, at least for human eye. So this is a typical idea of lossy data compression. Some data are thrown away, but still the resulting data looks similar to the original one. And the rate distortion function describes the fundamental limit of compression in such data compression method. And if time permits, I will explain more precise definition of rate distortion function, but now I want to skip it and goes to Brody curves. And we need to introduce one more quantity, rate distortion dimension. So we define rate distortion dimension by this formula. So this is a rate distortion function with respect to the threshold epsilon. And we divide it by log 1 over epsilon and take the limit. This quantity was first introduced by Storm Kawabata and Amir Dembo. So Kawabata is an electrical engineer and Dembo is a famous probabilist. Okay. So now we have the following theorem called variational principle. The mean dimension of the space of Brody curves is equal to the supremum of this rate distortion dimension. So the left-hand side is a topological invariant introduced by Gromov, and this in the right-hand side is some somewhat mysterious quantity introduced by some information theorist. All right. So if we take the supremum, then this rate distortion dimension is equal to mean dimension. Okay, so again, this is a mean dimension formula. Now this becomes this formula. So the left-hand side is the supremum rate distortion dimension, and the right-hand side is the supremum of some integral of potential function C.
Can you back up for a second? Is there any chance that equality is true if you remove supremo?
Oh, and I want to discuss it in the next section. Yeah. So, very nice questions. So this is a formula. The left-hand side is the supreme rate distortion dimension, and the right-hand side is the supreme some such integral. Then a natural question arises. What is the relation between this rate distortion dimension and the integral for each individual measure mu? This is a new question. And before going into the solution, I want to look at some examples. So let lambda be a lattice with this parameter L. And let F be a lambda periodic Brody curve. For example, some Weierstrass pair function, something like that. Then the orbit of F is a periodic orbit in this space of Brody curves. So let mu be the uniform measure on this periodic orbit. Then it is easy to see that rate distortion dimension is equal to 0, while this integral is equal to this quantity. And this is usually positive. So in other words, so rate distortion dimension and this integral are not necessarily equal to each other. And let's look at another example. Actually, this is the same as the previous example. So we take two parameters L and A, and let mu be the distribution of this random meromorphic function. So where parameter W and u lambda are independently and uniformly chosen from this square and this unit disk. In this case, we can show that the rate distortion dimension is equal to 2 over L square, and this integral is equal to 12 over L square. And again, so rate distortion dimension is strictly smaller than the integral of this quantity, this integral. Okay, now I can show you our main result. Main theorem 1. For any invariant probability measure mu on the space of Brody curves, its rate distortion dimension is always bounded by this integral. This is our first main result. And we will see later that this inequality is somewhat analogous to Luell inequality of smooth algorithmic theory. I want to call this inequality Luell inequality for Brody curves. This is the main theorem 1. This is main theorem 2. Main theorem 2 claims that there are many invariant probability measures attaining the equality in the previous main theorem 1. More precisely, let's see the real number between 0 and this quantity. There is some probability measure mu, invariant probability measure mu, satisfying this equation. The rate distortion dimension is equal to this integral, and it is equal to C. So there are uncountably many measure mu attaining the equality. Then combining main theorems 1 and 2, we can easily see that this equation follows. So main theorems 1 and 2 gives a somewhat deeper understanding of our mean dimension formula. These are the statement of main result. Is there any question so far? So let's discuss some proofs. The proofs of main theorems 1 and 2 are motivated by the so-called thermodynamic formalism for axiomatic diffeomorphism. So we want to review some of its idea. And this theory is a very significant theory developed by many important mathematicians, but probably the most important contributors are Sinai, Ruel, and Bowen. So sometimes called SRB theory. So this is a smooth ergodic. This is a story of smooth ergodic theory. Let M be an arbitrary compact Riemannian manifold with some axiomatic diffeomorphism T. And the axiom A means that the non-wandering set of T is hyperbolic, and the periodic points are dense in it. Let omega be a basic set of T. So what is basic set? So the precise definition is somewhat difficult, but basically, so the non-wandering set has some natural decomposition into some basic pieces. And each basic piece is called basic set. Let this equation be the splitting of the tangent space into stable and unstable directions. So this ES is a stable direction, and mu is the unstable direction. The simple example is this way. So simple example is given by this two-dimensional torus. Let M be a two-dimensional torus with a so-called hyperbolic toral automorphism, for example, this formula. And in this case, the non-wandering sets are equal to the total space M, and actually the basic set is only one set, and the basic set is also equal to M. And this is the eigenvalue decomposition of the space R2, and this provides a stable and unstable direction. This is a stable direction, and this is unstable direction. This is a very simple example of axiomatic diffeomorphism. We define a potential function phi on this space by this formula. So this is a logarithm of the Jacobian in the unstable direction. So we want to have the volume is stretched. So in the unstable direction. Now the fundamental equation in this theory is the following. We consider this, first we consider this quantity. This is the Kolmogorov-Shinai entropy minus this integral. Then take the supremum with respect to all T invariant probability measures on this basic set. Then it is known that this is equal to so-called topological pressure with respect to the potential function minus phi. This first equation is so-called variational principle, and this is a very general result. And the fundamental result specific to the axiom A case is this inequality. So this quantity is always less than or equal to 0. Then now it is easy to see that, so we consider this supremum and it is non-positive. So it means that we have this inequality for all T invariant probability measure mu. And actually, this is a special case of Ruel inequality. In general case of Ruel inequality, this right-hand side is an integral of so-called the sum of positive real proof exponents. But in this case, it reduced to this simple quantity. And moreover, if omega is an attractor, for example, so that in the case of hyperbolic total automorphism, omega is a total space, so it's obviously attractor. Then if omega is attractor, this equation is equal to 0. And actually, this is a characterization of the attractor. This topological pressure is equal to 0 if and only if omega is the attractor. And moreover, there is a probability measure mu attaining the supermem. So this measure mu is called Shinai-Ruel-Bowen measure. So it satisfies this equation. This is a very brief review of Shinai-Ruel-Bowen theory. Is it okay? And I want to establish some analog of this theory for Brody curves. So first, we need to define a quantity analogous to topological pressure. So mean dimension version of topological pressure. And it is called mean dimension with potential. So this is a general theory. Let XD be a compact metric space with some continuous function phi on X. We define the width dimension with potential phi by this formula. This is a bit complicated formula. So here P is a simplicial complex and F is a epsilon embedding from X to P. And we consider this some mysterious quantity. So first term is a local dimension of P as a point of X. Local dimension is this local dimension means that this is a dimension of some small neighborhood of Fx. And plus potential term. It takes the limit, takes the maximum with respect to the point X. And the infimum over all these P and F. If the potential function phi is 0, this reduced to our previous definition with this dimension.
Can we consider this as some kind of tropical version of the definition? Can we consider this as some tropical version of the rule, thermodynamic formalism?
Tropical version.
Plus is multiplication and max is plus, and then looks much closer to the thermodynamic formalism definition. Right? Because anyway, we can.
It's a very interesting idea.
Well, we're doing exactly something like that.
I want to know it. It's a very interesting idea. Thank you. Okay, so now we assume that there is a continuous action C on X. So X is a compact metric space, and let T be a continuous action C on X. Then for any positive number R, we define new metric dr and the new function phi r on X by these two formulas. So dr is just a Bowen metric, and phi r is integral of phi over the orbit of point X. This is just the standard two-dimensional integral. Now we define mean dimension with potential by this formula. This is a width dimension with potential, and we divide it by pi r square and take the limit with respect to r and with respect to epsilon. So this plays a similar role. So this plays a role similar to topological pressure theory. Okay, so let's go back to Brody curves. So recall that Pn is a space of all Brody curves in CPN, and it has a natural group action denoted by T. And we introduced a metric D on Bn by this formula, and we also introduced a function C by this formula. So this space has a group action and a metric and a function. So we can consider its mean dimension with potential. And the fundamental equation for our theory is the following. We consider this is a ray distortion dimension. Ray distortion dimension minus some potential term, and take the limit. Take the Shupin with respect to all invariant probability measures. Then we can prove that this Shupin is equal to the main dimension with potential for the potential function minus c. And in this case, this is equal to 0. So I think this is very similar to the Sinai-Ruel-Bowen theory. So in the case of Sinai-Ruel-Bowen theory, this term it becomes a Kolmogorov-Sinai entropy. And this term is equal to, this term corresponds to topological ratio. And it is equal to 0 in the case of axiomatic attractors. Okay, now so we have this equation, and it is easy to see that this equation implies our first main theorem. So ray distortion dimension is always bounded by this integral. And moreover, by investigating the proof of this fundamental equation more precisely, we can actually check that there is plenty of invariant measure mu containing the supremum of the fundamental equation. Namely, it's the measure mu satisfying this equation. So this provides main theorem 2. So this is a very rough sketch of the proof. Okay. So one important remark. There is a very important difference between axiomatic attractors and the case of Brody curves. In the case of axiomatic attractors, it is known that the Sinai-Ruel-Bowen measure is unique. On the contrary, in the case of Brody curves, there is plenty of measures satisfying this equation. So unfortunately, it seems that there is no way to select one distinguished measure for Brody curves. There is many nice measures, and there is no way to select one best measure. So this is a very rough sketch of the proof. How much time is left?
You have about another 10 minutes.
Okay, so I can explain some idea of ray distortion theory. So I didn't explain the precise definition of ray distortion function. So let's look at it here. Let omega p be a probability space, and let xi and eta be random variables defined on this probability space omega. And we want to define the mutual information I xi eta. And schematically, it is like this picture. So the left disk is information of xi. And the right disk is the information of eta. And we want to calculate the amount of information shared by xi and eta. It is called mutual information. Of course, this is a very standard quantity. I have no originality about this definition, of course.
Why is it called H?
What?
Why is it called H?
H is a Shannon entropy. The definition requires 2 steps. First, we assume that this xi takes value in the space X, and eta takes values in Y. And in the step 1, we assume that these spaces are finite set. Then we can simply define the initial information by this way. It is a sum of Shannon entropy of xi and the channel entropy eta minus the channel entropy of the joint distribution of Guzai and eta. And in general, so general means that X and Y may be infinite set. In this case, we define the mutual information by this way. Here, alpha and beta run over all finite measurable partitions of X and Y. Then this the composition of alpha and Z, composition of beta and eta are random variables taking only finitely many values. So this quantity is defined by step 1. This is the definition, mutual information. Now, so we want to define rate distortion function. This is a very general theory. Let XD be a compact metric space, and let A be some bounded C, so or some Borel set of C with finite measure, finite Lebesgue measure. And we define the space of L1AX as a space of all measurable maps from A to X with this natural metric. And suppose we are given a continuous action C on X. Let mu be some T invariant measure. For positive number epsilon, we want to define rate distortion function denoted by RD mu epsilon. Definition is somewhat so very abstract. So let A be any bounded set with positive measure. First, we define this quantity denoted by R epsilon A as the infimum of the mutual information where Xi and eta are two random variables defined on some common probability space such that Xi takes values in X according to the distribution mu, and eta takes values in this space L1AX such that the averaged distance between the orbit of Xi and eta are smaller than epsilon. So roughly speaking, so this TU Xi are some stochastic process, and we want to discretize this process by using eta. And this inequality means that the distortion of this discretization is small. Now we define the distortion function by this form. So here, this A is equal to the square of side length L. And we consider this quantity and divide it by L squared and take the limit. This is so-called rate distortion function. It's a bit abstract theory, but anyway, this is a very well-known theory, and I have no originality about this theory. Very classical theory. Okay, finally, we define rate distortion dimension by this formula. So we divide this rate distortion function by logarithm of 1 over epsilon and take the limit. This quantity is introduced by Kawabata and Dembo. Their original motivation is somewhat connected to fractal geometry. They want to, Kawabata and Dembo want to study the signals taking values in some fractal set. And then introduce this rate distortion dimension. Okay, so this is a precise definition, rate distortion function, rate distortion dimension. Maybe this final section is a bit abstract. Okay, so this is the final slide. Conclusion. So first, in my talk, we study invariant probability measures on the space of Brody curves. And we show that they satisfy a certain inequality analogous to real inequality of smooth algorithmic theory. And third, So we can construct a rich variety of measures attaining equality and this real inequality for Brody. Hopefully this is just a tip of iceberg, and maybe a bigger picture should be something like this. We can consider fusion of the idea of hyperbolic dynamics and some idea of geometric analysis. Maybe. Okay. That's all.
Very interesting talk. Any more questions?
Elliptic functions or doubly periodic functions have a special role in theoretical curves. For example, that they extremize certain natural quantities, or that there's something along the line of stochastic optimization, you know, where periodic orbits play a special role.
Say again? Sorry, I cannot understand.
Elliptic functions,
Yeah.
doubly periodic
Okay.
functions, play a special role. For example, that they maximize certain quantities.
So actually, it is related to your work. So it's so